screen. Okay, so today I want to talk about dark matter distributions around black holes and the implications for indirect detection. So I'm sure everybody's seen this type of pie chart. I'm going to be focusing on the dark matter portion of the pie chart. And there are different ways that we go about trying to detect dark matter. Here I have a diagram that shows direct detection and also a diagram on the right that shows collider searches. And to date, there's been no definitive signals from these types of searches. And in the absence of a signal, this also puts constraints on dark matter particle models. But today I want to focus in particular on indirect detection, and in particular on Fermi-Lat data, which I have a picture here shown on the right. And so for the Fermi-Lat data, it's essentially just a gamma ray spectrum of the sky. And the idea is that if we find sort of an excess somewhere, this has certainly been true for the Milky Way, the center of the Milky Way, there's an excess of gamma rays. We go and try to explain it by saying dark matter annihilates. And then possibly through some intermediate steps, finally you reach gamma ray photons. So we can explain the excess using these gamma rays. So I want to talk today in particular about dwarf galaxies and the idea of if there is a central black hole, the potential well from the black hole can cause a spike in the dark matter density. And this spike can enhance the gamma ray signal. And so there may be possibly indirect detection signals coming from this consideration. So I just wanted to briefly on one slide give the results of a CDM scenario. I don't want to go through the derivation because I want to focus on self-interacting dark matter, but I just want to have sort of in the back of our minds what happens in CDM. So in CDM, numerical simulations show that you get an NFW profile.
Jerry?
Yes.
Just a quick comment that because your background is deep blue and the words are in black, I'm not able to see any words actually. Can you make it white? I'm not sure other people, yeah.
Is that better?
Yeah.
Sorry about that. I don't know if I can change these equations.
No, equations are hard to change, I think.
Yeah.
You have to do latex or something. But if you have further equations, you may want to change the background color, I think.
That I'm not sure if I can do that. I'm not sure. So I'll try to change letters as I go to white.
Oh, no, you see, go down the background, you know.
Yeah, I'm not sure.
Mouse, yeah, your mouse. No. Go to the right. Yeah, you can change it. No, you move your mouse down on this IO. Yes, something like that.
Okay, let me see. Let me change it to. Yeah, if I change it to white, then I'm going to need to use the black letters again. Yeah, so maybe I will change the other ones to the background to white. But since I changed the letters here to white already, I'll just leave this slide. But okay, so yeah, so for CDM, starting with an NFW profile, an initial NFW profile, in the presence of a central black hole, it can be derived that you get a spike profile that goes as r to the -7/3. There are some caveats to this. So this assumes that the black hole forms adiabatically and also that the black hole forms in the center of the halo. So if the black hole were to form through mergers, the mergers can make the spike profile more shallow, and it could also erase the spike profile altogether, depending on the history. And also if the black hole forms misaligned off center from the halo, this will also soften the spike profile. And the last mechanism that I wanted to mention is that there's also the possibility of gravitational scattering between dark matter and the stellar population. And these gravitational scatterings can thermalize the halo, and this thermalization process will also soften the spike profile. But as I mentioned, so let me try and see if I can change the background here now. So yeah, so as I mentioned, I wanted to focus on dwarf galaxies, in particular satellite galaxies, um, and even more specifically on Draco in a few slides. But so for dwarf spheroidal systems, they are dark matter dominated. So the stellar population may be too small for this gravitational scattering mechanism to actually work. So we don't really expect the halos to thermalize in CDM for dwarf galaxies. However, we consider self-interacting dark matter. The self-interaction between dark matter particles, the scattering can naturally lead to a thermalized halo. Um, so I wanted to go over, or at least sketch, the derivation of the spike profile in the SIDM case. So I just start off with the definition of the density as just an integration over the phase space distribution, where I integrate from zero velocity to the escape velocity. And this is because I'm only considering bound particles. And because we expect the halo to be thermalized, I just assume that the phase space distribution is a Maxwell-Boltzmann, where we have a normalization parameter, rho naught, and we also have what is typically referred to as a 1D velocity dispersion, sigma naught. There's some subtlety there that I will mention in a few slides. But the important part is that if we focus on the very central regions, I can write the energy in the Maxwell-Boltzmann as this expression here, where this is the energy per unit mass, where the gravitational potential is dominated by the black hole. So we ignore any baryonic contribution, which we expect to be small in dwarf galaxies anyways. And we also ignore the dark matter distribution. So this should be valid only in the very central regions. And I also have here the definition of the velocity dispersion. So if I put all these pieces together and I carry out the integration, I get expressions that look like this. So for the density, it's something that involves error functions. This R sub BH is what is referred to in the literature as the sphere of influence of the black hole. So I have it defined on the next slide. But here's just a parameter which basically tells you when the black hole's gravitational potential becomes important. And so if we look at the limiting behavior of this function, you can sort of extract some physics. So if we look at the very small r expansion of this expression, we get something that diverges exponentially. And if we look at large r behavior, we get a profile that goes r to the minus 3/2. And so this is what we extract as the spike profile. So for SIDM, this is much more shallow than for the CDM case, which was minus 7/3. And so this becomes very important for indirect detection. You can also find analytically the velocity dispersion, which you get this sort of complicated function. And again, if you look at the limiting behavior in the very extreme inner regions, you get a constant. But if you look at the large R behavior, you get something that goes 1 over R. So I have here plotted on the left, the density is a function of the radius with some normalization parameters. And I have in gray dashed line the r to the minus 3/2 power. So you see for the large R behavior, it follows the minus 3/2 power pretty well. But in the inner regions, you get an exponential divergence. And I have also the velocity dispersion plotted in sort of a funny way where it's normalized by the gravitational potential. And this is due to the fact that if I plot things this way, this sort of shape is true for any black hole mass. Otherwise, I'd have to put in a specific mass. But it's plotted over different 1D velocity dispersions, and the profiles look essentially the same. It just shifts either left or right. So I promised I would define the sphere of influence here. So it's just given by the black hole mass, Newton's constant, and whatever the 1D velocity dispersion is. And on the right-hand side, the normalization, our bar is just a fiducial radius that we take to be much larger than the sphere of influence. Up until this point, I haven't considered annihilations. So if we consider that the dark matter annihilates, then we have to, this can change the profile because if dark matter is annihilating, you're getting rid of dark matter particles, and this will soften the density distribution. So the way that we account for this is we define what's called the annihilation density, which occurs at the annihilation radius. And this basically just tells you when the annihilation rate becomes once per age of the system. So here I have T age, it's the age of the halo, I have the dark matter mass, and the thermalized annihilation cross-section. And so if we're interested in regions are much larger than our annihilation, we say that all dark matter particles contribute to the phase space density. And this is because if we're outside the annihilation zone, we're going to make the assumption that the particles completely escaped annihilation. On the other hand, if we look at the R less than our annihilation, so here in this diagram, I have this dotted red line supposed to represent the annihilation radius. So if we're looking within the annihilation zone, then we have to ensure that the particle's orbit, at least in some part of the orbit, goes outside the annihilation radius. Otherwise, we assume that the particle has annihilated in the age of the system. So for example, this blue orbit here, I would say that this particle doesn't contribute to the phase space because it's completely contained in the annihilation zone. This green orbit, I say it does contribute, and it does contribute because at least partially the orbit is outside the annihilation radius. So even though there is some possibility that, some of the orbit is still in the annihilation zone, so there is a possibility that this particle can annihilate. But there's arguments to say the particle moves more slowly out here, spends more time out here. So we just make an approximation and we say that the particle has completely escaped annihilation. So we have to ensure that that the particle has enough velocity to at least reach the annihilation radius. So we define this velocity v annihilation, which is just solved by setting the energy to the gravitational potential at the annihilation radius and solving for v. So in the distribution, the way that we account for these changes is we just say, okay, it's the same definition for density, except now I have to ensure that I have some minimum velocity, where if I'm outside the annihilation radius, I still account for all velocities. However, if I'm within the annihilation zone, the minimum velocity must be at least v annihilation. Again, I plug it into the integration. I go through the steps, crank the mathematics, and what I find is for the large R behavior, nothing changes. It's still r to the minus 3/2. But for small r, I get an r to the minus 1/2 power law. So this is also known in the CDM paradigm. It's called the weak annihilation plateau. So this is actually a result, which is a generic result. And if you can write your phase space distribution as power laws in E, then for any power, this result holds true. And for a Maxwell-Boltzmann, you can always expand the exponential in terms of power laws in E. And so this is also true for SIDM. What we find for the velocity distribution for small r is no longer a constant if we consider annihilations. And this might be a little troubling at first because we're assuming isothermal distribution, and now we're saying the velocity dispersion is not a constant. But I think the important point is that temperature needs to be a constant for isothermal, and temperature is a measure of the dispersion in energy. And now because there's gravitation, there's energy in the gravitational potential. So now we can't really equate what is normally called the 1D velocity dispersion. We can't really equate that with a dispersion in velocity alone. It's really a dispersion in the total energy. So that introduces some radial dependence. So I have the plots here, including annihilation. And so we see the dotted lines here correspond to the exponential divergence if there were no annihilations. And we see if we introduce annihilations, we get this r to the minus 1/2 plateau. You can still get an exponential divergence near the annihilation radius if your 1D velocity dispersion is less than the gravitational potential at the annihilation radius. But through the virial theorem, we expect this to be an order 1 number in front of this potential. So the exponential divergence should be not so strong. And we see that in any case, the large R behavior is always an r to the minus 3/2. I also have the velocity here on the right, and the difference here is that it is no longer vanishing in the inner regions, and this is what gives you a 1/r dependence because of this weird normalization in the plot. So, okay, so for indirect detection, what's important for indirect detection is we need now the extended halo. We have to consider the entire halo now, not just the central region. So the way we get the extended halo for an isothermal distribution is we use the Jeans equation, which is just essentially the Poisson's equation for gravitation combined with some thermal equilibrium equations. And we just piece this together in a piecewise fashion to these central regions that I just derived. And the point in which we piece it together, we call it the spike radius. And the spike radius is some factor of the sphere of influence, except here we derive the sphere of influence in sort of a different way, an alternative way, where we integrate the distribution and we find at what point essentially the mass due to the halo is comparable to the mass of the black hole. And then as some fraction of that, we say the black hole dominates the gravitational potential, and then the expressions I derived a few slides ago then become valid. And just for simplicity, what we do is we stitch on these profiles that look in this form, which are essentially just the power laws I derived. So we kind of ignore that exponential divergence that can possibly occur at the annihilation radius, and we just assume simple power laws. So the way that we can calculate the signal coming from annihilations is through these expressions here, where for the extended halo, it depends on this J factor. And this J factor is essentially a line of sight integral of the density squared. And for the spike signal, it depends on this Q factor. And this Q factor is something similar. It's still density squared, but it's weighted by this R squared as well. And for the Q factor, we only integrate from the annihilation radius to the spike radius. And the reason we do this is because the annihilation radius is typically extremely small in the very, very inner regions. So there's not much volume there, so the signal, it doesn't contribute much. And also we expect a breakdown in the isothermal assumption very near the black hole due to GR effects. So due to the red shifting of space-time, we can no longer define an isothermal distribution. But within this region, we expect that the assumption is still valid. And this is where the majority of the signal is coming from. For the J factor, we integrate from some angle theta to some theta max. This just basically defines the resolution of your detector. And we integrate the spectrum, this DNDE. We integrate the spectrum from an energy 100 MeV to 100 GeV. And this just comes from the energy resolution of Fermi-Lat. So these are the parameters. The total flux coming from the dark matter annihilations is the sum of the extended halo plus the spike signal. We put all these pieces together, and what we find, so here on the left, we have a plot of the extended profile along with the spike power laws that I have here as a dotted line. The spike power law comes from a 10 to the 5 solar mass black hole. And these solid lines for red is the SIDM, so you see the isothermal core in the inner regions, and for black is just an NFW profile. And the larger R, about 10 kiloparsecs, we see a sharp cutoff. This comes from tidal stripping. So we use an R to the -5th, I believe, power law to account for the tidal stripping. So this is the extended profile we use to get our signal. On the right, we have our results for the annihilation cross-section as a function of black hole mass. And this is in particular for the Draco-Dwarf galaxy. So these profiles here in the left plot, the parameters are from data, the best fit data for line of sight velocity dispersions and things like that. So we get the best fit parameters. These are our plots. We plug it into the previous expressions on the previous slide. And what we see for CDM in black, it's sensitive to the black hole mass. So for instance, down here, as dotted black line, we have a 10 GeV dark matter mass. And we see this gray dotted line here represents the thermal relic that we typically expect for a freeze out scenario. So for 10 GeV, it's already pushing it really close, but it definitely drops below the line at about 10 solar mass black hole. So above 10 solar masses, we don't expect that the dwarf galaxy Draco can host a black hole and still be composed of thermal relic dark matter. For a 1 TeV dark matter mass, in CDM case, this is pushed to about 10 to the 3 solar masses. So in any case, above 10 to the 3 solar masses, we don't expect there to be a black hole and still a thermal relic halo. But for SIDM case, because the spike power law is much more shallow, it's essentially insensitive to the black hole mass. So this turnover doesn't happen for SIDM until about 10 to the 9 solar masses, 10 to the 7 solar masses, something like that. But this is more mass than the halo itself. So this is completely unreasonable for this system. So for any black hole mass reasonable for the system, it's insensitive to the mass of the black hole. So basically we show that for SIDM, you can have black holes in dwarf galaxies, where for CDM, essentially you cannot, and still be composed of thermal relics. So for future work, so for future work, we basically want to apply the results to M87, supermassive black hole. So this is the black hole that they took the picture, the Event Horizon Telescope took a picture. So there's been recent work in the literature claiming that the Event Horizon Telescope has extreme resolution, which can get some very stringent constraints on dark matter annihilations in the CDM context. So we want to see if we can weaken these constraints a little bit using SIDM. And so me and Haibo have estimated that we expect about a factor 10 to the 5 weaker constraint in the SIDM case than in the CDM case. But there's more work to be done. So in conclusion, SIDM is a well-motivated particle physics model and is less constrained in general and indirect detection considerations in the CDM counterpart. It's exciting to think about the M87, the consequences of M87 and sort of this new frontier of high resolution black hole images. And in general, SIDM spikes may also play an important role in seeding primordial black holes. So that might be an interesting avenue to search as well. And that's all I have.